Okay, thank you. I'm Damien Freulich, and I'm presenting a language-parametric approach to exploratory programming. This is joint work with the Vrije Universiteit in Amsterdam, and also the REN University and the CWI from Amsterdam. So what is exploratory programming? It's a programming style in which the goal we are working towards is not fully known yet. So by experimenting with code, this goal becomes more concrete. And this requires us to maybe try out many different versions. So it's a volatile style of development. And we might create code that will not be used in the end product. So we just use it to come to a conclusion of what our goal is, and then we throw it away. So environments in which we program should support this kind of programming by making it easy to create new versions and to compare different versions with each other. And here we see an example of a small questionnaire language. So on the left side, on the top, you see the language. We can create forms and have questions that interact with the user, and this then creates an application that we see on the left bottom, where users can input values. And on the right, we see the trace of an exploratory session. So we start at the top with 3D, and then we have one form in which we ask what the age is. We then input the age, which we see, we set the age to 42, and then we create a new effect in which we give the output after this value is inputted, in which we say what the age times 2 is. So your age twice your age is this value. Then we click on the lightning bolt, and this creates a new version. So in this case, it's the 2A version, where we start off with the age, and then we add another input to our form. In this case, we ask the user, what is your height? And then based on the conditional value, in this case, if the height is bigger than 200, then we might show that someone is tall. Then we again click on the lightning bolt, create a new version, and here we integrate our result of adding height to our form into a new form, and that is the application we see on the left. So here we see that by clicking on the lightning bolt, we create many different versions, and now what is possible is we can compare these different versions and click through them and just try different styles out. And over the last couple of years, there have been new development of exploratory environments that support this kind of development. And on the slide, you see two. So one is Variolite. This is an integration into the Atom editor. And what they allow you to do is select pieces of text and then create new versions. And then you can quickly switch between these two different versions inside the editor. The other one is microversioning. They basically track all edits you make. And then over a certain period of time, they make a micro version of that edit, and then you can quickly switch between different micro versions. And what both these environments have in common is that they're based on text-based environments. And text-based environments are nice because they're easily used between many different languages. It doesn't really matter which language you use if it's text-based. However, the interactivity is a bit low because when we switch to a different version, we might have to execute a common prelude or previous code to get to the runtime state of that piece of code. And when this piece of code takes a lot of time, it might become a bit slow to change between versions. It also doesn't really offer any inspection into the runtime state. So in the questionnaire language, we clearly saw different semantic deltas and saw how it changed the forms. With text-based environments, we don't have this runtime state inspection as nice as with executable environments. So executable environments are exploratory environments which are based on the execution level, so they basically keep track of the runtime state in a graph or in a tree. And this makes it easy for the user to jump between different versions. And then this gives us high interactivity because we don't have to re-execute the code, all the code when we switch to different versions. The disadvantage of executable-based environments is that for every language, we need to create an implementation. It's not as easy to create an exploratory environment as in the text-based approach. And that is where this talks focus on. So let's say we have a couple of exploratory environments that talk with a specific backend. So we might have 3 environments that talk with 3 different languages. Now, these environments all talk over a different communication protocol. So that is useful. But the last environment is very nice, and we want to reuse this across the other backends. Now, the problem is these backends, they don't talk the same protocol. So now this front end has to implement 3 backend protocols to talk with those different backends. And now if we want to do this for the other front ends as well, we have to implement these protocols again and again. This is basically the n times n problem, and we see that also with compilers, where we, for example, have source languages that compile to a specific target language. In that case, we can use an intermediate representation that is shared, but we also see it with code editors, where we now have the language server protocol that kind of functions as a common communication protocol. And that is similar what we want to achieve. So we need a structured approach for exploratory-based environments in a language-independent manner so that we can quickly create exploratory environments for different languages and explore with novel features for these environments. And to that end, we present an architecture for the creation of language-parametric exploratory environments. This architecture is basically split up in two pieces. We have a front end and we have a back end. The front end contains an interface and a client and client bridge. And in the architecture, the dashed rectangles, they are language reusable, so they are reusable across languages. And the solid rectangles, they are language specific. So they are essentially the parameters into our system. And the backend contains all the pieces of code needed to actually make it executable. And we have a server. So let's take a look in these components in a bit more detail. The first being the exploring interpreter. This is essentially the engine adding support for exploratory programming to our systems. And this is based on previous work in which they investigated the read-eval print loop and tried to find out what the underlying formalisms are for read-eval print loops. And they found that basically all REPLs, they kind of implement the class of sequential languages. And a sequential language is a language in which we can take any two programs, sequence them together, and then we have a new valid program. And when we interpret the sequence, it should have the same effect as interpreting the two programs in isolation and composing that interpretation. And in this case, the interpretation is a function for every program from configuration to configuration, where the configuration contains all the necessary information for subsequent executions. They also introduced the idea of REPLization. This is essentially a structured approach to take an existing language and turn it into a sequential language, for which we then obtain REPL environments for free. And finally, they introduced the idea of the exploring interpreter, which is essentially a bookkeeping device that keeps track of the execution graph, and it allows you to add support for exploratory programming. It has three main methods: execute to execute programs, which extends the exploration tree, revert to go back to other locations in the graph, and display to show the graph. So here I have an example of such an exploration tree for a little calculator language. So we start with our initial configuration. This is now also the current configuration. So the current configuration is highlighted with a dashed box. And then we execute a simple program. So we execute 5 + 2, and then we see that the first element in our configuration is updated. So this is the result. The second element is a store mapping identifiers to values. Okay, so we executed 5 + 2, and then we think, well, let's go back to the initial configuration. So we refer to 0, and this is destructive. So what that means is that the configuration where we referred from is now destroyed. So we can't go back to that configuration anymore. Then what we do is we execute a sequence. So in this case, the semicolon is the sequence operator. So we execute a sequence. These are just two programs. And we get two new configurations into our system. So the first program is we assign the evaluation of 5 + 2 to the variable x. And we see an update in our store component. And in the second time, we use the x variable and do ×2. And then we see an effect in our result component. And then we can also do this with non-destructive revert. And the difference here is that when we do a revert, the configuration is not removed. So it's still there. So in the case of non-destructive revert, we can easily jump back to the second configuration we obtained, where the result component was 7 and the store had no elements. And the advantage of non-destructive revert is that we have more exploration options, but it also takes more memory, and it can become a bit unwieldy when you have a lot of states. So by having destructive revert, you can manage this a bit. And we contribute to this idea by updating the notion of sequential languages. So if we look at the interpretation as it is now, it is essentially a function from configurations to configurations. But then what about failure? Well, we integrate that by either just interpreting the second program. If the first program fails, we just interpret the second program with the current configuration. If it doesn't fail, it's just the composition as before. Then we also have write-only effects. So essentially effects that do not affect the subsequent execution of programs. And the main example of this is output. And we integrate this by essentially making our interpretation function not return a configuration, but a tuple, where the first projection is again a configuration, and the second projection is output. Now a sequence is essentially just interpreting the configuration as our original case, but now output is concatenated together, and that becomes the output of the sequenced evaluation. And then what we do is we combine these two extensions into an extended form of sequential languages that support both erroneous computation and output. So it might be that you have an erroneous computation, but that still produces output. So that's why we extracted this output component out of the configuration. So even if you have failed computation, you can still show error messages, and they are also available in your exploration tree. We also update the notion of the exploring interpreter. So in the original paper, they use a current configuration, an execution graph, and these different operations, where they made a decision to revert, to basically decide what kind of revert you use when you start up the system. And we instead take an approach of keeping an execution tree instead of a graph, because it's easier to reason about when you have a tree. Because with a graph, you might create paths that are not actually in your exploration session. And we take the decision to split revert into two operations. One is the destructive revert, and one is the jump, which is non-destructive. And now the user can just decide what to do with the exploration tree and maybe trim it when they don't need an exploration part anymore. So these exploring interpreters can be derived for any language that follows our definition of language for free. So we don't actually have to do anything. Then, to communicate with the backend and the front end, we created the exploratory programming protocol, and this is essentially just an version of the language server protocol, but then focused on exploratory programming. So it's based on JSON RPC, it's defined using TypeScript interfaces, and it extends the base of the language server protocol. And the rationale behind this was to either be able to extend the language server protocol with this support, or to have it run alongside the language server protocol, where servers that implement the server protocol can say, okay, we also implement the EPP without having to introduce another notion of protocol. And here we see an example of our protocol. Essentially, we just have request messages which have an ID to keep track. It has a method and it has optional parameters. And then we have, in this example, our execute request, which has as the parameters a program that we are executing. And then we also have responses. They have an ID that match up with the corresponding request to allow us to match responses and requests to each other. And they either have a result or an error. And in this example, we have our execute result, in which we have the source and the target. So we have our tree, and the source is essentially where we started from. The target is where we ended after the execution of the program. The output is along the label, so that's the output produced by the program. And we also have optional post-processing information. Post-processing information is information that is specific to languages, and this can, for example, be used to extract information out of the two configurations, so the source and the target. This allows you to, for example, see the effects a program had on the configurations. And these are the main methods we have. So we have our three main methods, which are essentially execute, revert, and jump. And then we have a bunch of auxiliary methods that are used by interfaces to, for example, display the tree or get configuration information displayed to the user. And we have also the option to execute meta commands. So meta commands are commands that execute on top of the exploration tree, but they cannot modify it. So one reason we use this is to implement semantic search. We essentially perform a search over the exploration tree and find all configurations in which, for example, a function of identifier is defined. This can then be reported back to the front end, but the exploration tree is not modified. So then back to the reusable architecture, we have a server component which essentially transforms the exploratory programming protocol into actions on the different components in the backend. So in our execute request, we get the execute parameters in, we call the parser with a program, and this either gives us a program that we can give to the exploring interpreter, or it gives us an error. If it's a program that we can use for the exploring interpreter, we call the exploring interpreter. This calls the definitional interpreter, so that actually implements the language, and we update the execution tree and respond back to the client, to the front end. Then we have a client bridge. This is essentially just a layer of indirection to allow us to have the front end split across multiple machines. This is used in our example, in our implementation. This is used to implement an HTML front end that communicates via WebSockets. So essentially, the client bridge runs on one server. This communicates with the client over WebSockets, and then the client bridge communicates with the server over just a normal socket over the exploratory programming protocol. And you can also implement the client bridge as just a component inside your client. Then it's just function calls, but it can also just be an HTTP client. So it's just a layer of interaction to make it possible to have the front end split across multiple machines. The client is just a way to transform the EPP into actions on the interface, and the interface is the final meat of the system. This essentially is the thing that is displayed to the user, and it's how the user interacts with the environment. So we have eventually developed a couple of interfaces on top of this architecture, and the top interface is the one I want to show. We essentially looked into the literature at what kind of features exploratory programming environments need based on surveys done with developers that use this kind of programming. For example, in data science, but also general purpose programming. And we integrated this into our experimental notebook front end. So essentially, we have 3 panes. On the left pane, it's a bit similar to a Jupyter notebook. We have just code cells and also documentation cells. You can put code into it, and then you execute it. And in the middle pane, we have an execution trace. So essentially, we're always in one trace in the tree, and that is displayed in the middle pane. And what we can do there is we can change one of the programs in our trace, and then modify it, and then re-execute it. So this way, it automatically executes all subsequent programs in our trace as well. So this way, we can create a small variation and then see how it affects an existing exploratory session easily. And on the right side, we have a pane of head nodes. These are essentially the leaves in our tree, and this allows us to quickly switch between different traces to go to earlier exploration sessions, or we can select these traces, select these nodes, and compare them. This way, we can, for example, compare traces and see how different design choices affected the program. And that is what we show here. And here we also have the option to search. So we can, for example, search configurations in traces and see how they affected the exploration session. Then this is eventually the architecture we support and provide. And it's reusable in many components. And we have implemented it for a variety of languages. One language is Idris, which is the dependently typed programming language. And it is not developed by us. So a couple of languages we implemented was developed by us, essentially to our approach, but Idris wasn't. It was completely developed without anticipating our use case. And eventually, it took us around 5 lines to transform the Idris interpreter into an interpreter as we expected. So most work was into defining the JSON instances to transform Idris configurations into JSON instances. So to actually modify the Idris interpreter to our approach was interestingly not that much work. So now we have these implementation. We have this architecture that is reusable. We want to use this to continue investigation of language-parametric interfaces, especially language-specific widgets. So currently, our interfaces are very generic. They do not take many assumptions, so they can be reused by many languages. But it's also useful to have, for example, widgets that are language-specific. For example, in Idris, you can do proving. That might be something that can be a language-specific widget. Another example is parametric widgets. We have implemented a couple of those. One of that is the search. So we have search over configurations. In the default case, this uses search over the DOM. But in case a backend implements semantic search, it can instead use the semantic search and do search on the backend over configurations. We also want to integrate the protocol with the Jupyter Notebook and see how that affects essentially exploratory programming inside Jupyter Notebooks, and explore exploration recommendations. Because when you do a long exploration session, you might get a lot of configurations and you get a lot of traces. And this might become a bit overwhelming when you want to see what the results are. So we want to see if we can find possible traces that we can recommend to users if you're working on a specific trace, and then say, this trace is also available and you might want to look at it. So yeah, with this reusable architecture, we have experimentation with novel features for exploratory programming in exploratory environments, and it can be applied to a large class of languages using the generic protocol. Thank you.
Do you have any questions from the room? All right. So you demonstrated pretty nicely that it takes basically no effort to implement a new language.
Yeah.
I assume okay, so that was specifically for helping the part, but so you have to implement all that the JSON infrastructure.
Yeah.
Right?
So essentially, what we have to do there is we have to. So in certain cases on the front end, we want to see the state of configurations. So what is in there, and to do that, we had to write JSON instances for the configurations. And it also requires us to write JSON instances for the programs and all possible values inside the configuration.
So I suppose that's in the implementation language of Idris, right?
Yes, so that is in Haskell in this case. Yes, exactly. Yeah. Yeah, sure.
Yes, so you mentioned that you're able to do this for a class of languages that you and Thomas.
Yeah.
Can you elaborate a little bit? What is this class of languages?
So it's essentially languages that can be implemented by a transition system. So we assume that these languages have an underlying transition system in the form of a definitional interpreter, and if that's the case, it can work in our system.
They are not that much.
What?
So they are not that much.
I think they are pretty much. Like many languages can be defined in structural operational semantics, and in that case, it can work in our approach.
All right, do we have the last question from this in the room or from online? Okay. Thank you, Damian, for your talk.
Thank you.